Another example of utilizing a triple integral to be able to, or evaluating a triple integral, we want to evaluate the triple integral of x dv over some region bound by a paraboloid x equals 4y squared plus 4z squared and the plane x equals 4. So to be able to figure out what we might want to do with this, it might be helpful for us to go ahead and to be able to draw a diagram of this. So in our diagram, now I want you to notice that our graph is a paraboloid. Okay, so what we have here is we certainly have a paraboloid, but it's going to open up on the x-axis. Okay, so that's our paraboloid, and certainly this is a plane. So if I was to draw this, okay, so let's say this is our x-axis, our y-axis, and our z-axis, right? Then we would have a paraboloid. It would open up along the x-axis, okay, so we get something like this, approximately. And then we'd also have a plane x equals 4. Now x equals 4 is going to be this plane, and it's going to look like this. Okay, so basically what we're doing is we're essentially taking a piece of paper and we're cutting right through our paraboloid. Alright, so this is the function x equals 4y squared plus 4z squared. Right? And then this is the plane x equals 4. So if I'm setting up this integral, then the first thing I might want to do is I might want to go ahead and say, okay, well, if this is the area that I'm cutting out, and kind of think of this as the volume that's bound up to the plane. All right, so let's say the plane just cuts through our paraboloid. So that means that the bottom of the paraboloid up to the plane are the bounds for x. So x is going to be bound by 4y squared plus 4z squared to 4. Right, so we're thinking this in terms of z, or I'm sorry, in terms of x. So at least we can set up the first part of it. Then we can worry about the rest of it. All right, so let's do that first. So now we have our triple integral, and x is going to range from 4y squared to 4z squared to 4. Now remember, x was going to be the original integrand. Okay, so we just have this x that we're bringing down there. All right, and we'll just say dx. And then the rest of it we're not sure about yet. Okay, so let's just do that first now, dx, and I'm going to call this a, and I'm going to say dA for the other part of it. Okay, because we'll be in 2 dimensions at that point. Okay, so if I evaluate this, then what I'd end up with is I'd end up with a double integral of some area A, 1/2 x squared, so I'm going to factor out the 1/2, and I have my x squared, and that's going to range from 4y squared plus 4z squared to 4. And we still have dA out here. All right, so if I set this up, then we can have 1/2 the double integral of some area A, and then we have, I'm going to put this in brackets, we have the quantity of 4y squared plus 4z squared squared, and then 4 squared minus that. So I think I've made that backwards. Sorry about that. So let me erase this. Right, so it's going to be 4 squared minus the quantity of 4y squared plus 4z squared, dA. And this is squared as well. All right, now, unfortunately for us, this is not going to be something easy to evaluate in terms of y and z. All right, I mean, we could certainly FOIL this out if we wanted to, but if we go back up, it seems that we have a really nice sort of paraboloid area if we wanted to. All right, so what we can do is, couldn't we substitute 4 back in for x, and we would get the relationship that 4 is equal to 4y squared plus 4z squared. Okay, or in other words, 1 equals y squared plus z squared. And remember that we have the relationship in polar coordinates that x squared plus y squared equals r squared. So let's think of this, because we've already evaluated the x variable. Let's go ahead and get rid of that, and let's think of z squared plus y squared as r squared. Right? So in other words, what we're doing is we're making this into a polar function, and we could do this double integral very nicely in polar coordinates instead. All right, except that now we're just using, instead of z, or instead of x squared plus y squared, we're just replacing x with z in this case, which is perfectly fine because now we're just on a different axis. All right, so we can say 1 equals r squared, which implies 1 is equal to r. So the bounds for r are 0 to 1. All right, and if you look at our paraboloid, clearly we can go from 0 to 1. Okay, so the radius is basically going to be 1 at its max when it touches the plane. And then finally, because it doesn't necessarily designate a quadrant, the range for theta is going to be 0 to 2 pi. All right, so now we can rewrite our integrand that we had all the way up top here. We can rewrite that as 1/2 0 to 2 pi 0 to 1. All right. Now remember we had 4 squared, which is 16. Okay, so that's this 4 square right here. And then instead of 4y squared plus 4z squared, couldn't we rewrite that as 4r squared square? All right. And I'll move down here, because remember we said that y squared plus z squared is r squared. So we just multiply everything by 4. That's going to be 4r squared squared. So that's going to be minus 4r squared square. All right, so that's from our substitution. And then we can't forget r dr d theta, because now we're in their polar coordinates. All right, now it becomes really easy to evaluate. Okay, I'm going to separate the d theta, so we have 1/2 0 to 2 pi, and then we just have our d theta. Then we're going to have integral 0 to 1 of quantity 16r, so I distribute the r to this 16, and then minus 16r to the 5th. And the 16r to the 5th comes from r squared squared, so that's 4, and then one more r from the distribution, dr. Right. Now it's just an elementary polynomial to evaluate. We're going to have 1/2. This just becomes 2 pi, as we've seen a number of times. We're going to get 8r squared minus 16/6 r to the 6th. And r is going to range from 0 to 1. The good news is that 0 contributes nothing to the entire sum. 1/2 and 2 are going to cancel out, so we get pi times the quantity, and I should have put a bracket up there, so pi times the quantity of 8 times 1 square. 16/6 is going to simplify to 8/3 times 1 to the 6th. Now technically there's a minus 0 in there. All right, and then if we compute that out really quickly, that should give us 16/3, I believe, and then we have a pi in there, but I'm going to verify that really quickly. So 8 minus 8/3 is going to give us a 16/3, and then we have a pi out there. So our evaluated integral is 16 pi thirds. Right? So go back, watch this again if you didn't quite get that. Suggestion would be to pay specific attention to the conversion into the polar coordinates along the x-axis as opposed to along the z-axis. All right, so we're just using our polar definition along a different axis, and that's going to make it able to evaluate this very nicely. Certainly, you could have done it the other way without polar coordinates, but that would have been much more difficult.